Okay, so let's get started. I'm very happy to introduce Jacques Distler from University of Texas at Austin, who's going to give the, 2 talks. So today we'll have an introduction to Class S and Tinkertoys.
Great, thank you. I'm going to give 2 talks about Class S. Which will also be the subject of talks by Lottie Holland, and I apologize in advance for the completely irresponsible lack of coordination between the 2 speakers on that, but this is the way life is sometimes. So what I'm going to be talking about is a large, but not exhaustive, class of D equals 4, N equals 2 superconformal field theories. And the data to specify one of these guys consists of a closed Riemann surface with n marked points, pi, I equals 1 to n. And I'm going to demand that C be stable. So n is greater than or equal to 3 for genus 0, and n is greater than or equal to 1 for genus 1. So that's one piece of data. The next piece of data is J, a simple Lie algebra of ADE type. And as a point of clarification, every Lie algebra I'm going to speak of is a complex Lie algebra. Every Lie group is going to be the corresponding compact real form. Okay, and don't ask me exactly what the global structure is, whether it's the simply connected or the adjoint or whatever. That level of subtlety will be well beyond our abilities for the next hour and 10 minutes, okay? But as I said, Lie algebras are complex, groups are compact, the corresponding groups are compact. Okay, so we have J. And then the next piece of data is a principal bundle on the complement of the punctures. Where gamma is the outer automorphism group of J. So gamma is Z2 for A, D, and E6. And it's S3 for D4, and it's trivial for E7 and E8. That's that piece of data. And then at each marked point, I'm going to decorate it by a nilpotent orbit in, I'm going to run out of space either way. I think we'll do it. In G, which is the Langland's dual of J naught, where J naught is the gamma invariant subspace, invariant subalgebra, where gamma is the holonomy of P restricted to the circle surrounding that puncture. Okay, it's specified by one element of the group capital gamma, and the invariant subalgebra of that guy, take its Langlands dual. That's what I'm calling Lie algebra G. Okay, so you have a nilpotent orbit in G. Sorry? This is little gamma. Gamma is an element of big gamma, which specifies what the bundle P is restricted to that circle. Right? Got it? Okay, so when P is trivial, of course, the restriction of the trivial bundle is always trivial. The invariant subalgebra is always the full algebra. And since this is simply laced, G is just J. Okay, so it's a nilpotent orbit in J. Otherwise, it's a nilpotent orbit in this other thing. So far, so good? Okay. So that's the data, and I'm going to try to leave that up on the blackboard. Oh, no, but let me say one more thing before I do that, which is clearly these theories for n greater than 3 or g greater than 0 come in families of dimension 3g minus 3 plus n. If p is trivial, you might think that the, well, we have the space of complex structures of the curve C and the locations of the points. So obviously that, you know, I get different theories depending on where I am in MGN. You might say this is for P trivial. When P is non-trivial, you might think we have something. So this is what we might call the. The physicists call this conformal manifold. So of course, it's not a manifold. I mean, it's singular. Maybe it's even a stack. Okay, because the conformal field theories come with automorphisms. Yes, sir. Sorry, this was an N?
No. I mean the last line there, P subscript.
The circle surrounding the ith puncture.
Right.
Right?
Thank you.
We removed the puncture, so we got a bunch of circles, and the holonomy of gamma around that circle is the holonomy of P around that circle is specified by an element little gamma of the group capital gamma.
Okay, thank you.
Okay? So you might think that in this case, what we get is the moduli space not of punctured curves, but of pairs consisting of a punctured curve and one of these principal bundles of gamma, these principal gamma bundles. But this is not quite right. And the reason is that in D2n, gamma acts on the set of orbits in J. So even if I have an untwisted orbit, right? These are the guys corresponding to very even partitions, if you know what that is. If I take that guy, drag it around some cycle on the curve C, where I have some non-trivial monodromy in the principal bundle B, bring it back to where I started, it's changed from one very even orbit to the other one. Okay, so it's this isn't quite right. Instead, what I get is some finite cover of this space, branched over the boundary of the moduli space. We'll come to that in the next lecture. I just put that out there as a caveat. I've gotten very technical. Before I start getting even more technical, I should pause for a second and try to talk about the big picture. This is often nobody bothers to do this, but I'm going to try. Why am I interested in this subject at all? And the answer is because, as a physicist, I want to understand quantum field theory. This is a monumentally difficult task. Naively, quantum field theory is the quantization of an infinite dimensional dynamical system in the way that quantum mechanics is the quantization of some finite dimensional dynamical system, where the infinite dimensional dynamical system is some classical field theory. So you might take Maxwell electrodynamics, and when you quantize it, you get quantum electrodynamics. Sounds easy, and it's really hopelessly, deceptively wrong. There are a lot of subtleties in dealing with this infinite dimensional case, even in this simplest of field theories. You have to regularize your theory in some way, impose some kind of cutoff. And when you do, you need to make sure, you need to go through some procedure to make sure that the physical observables that you compute are independent of your choice of regularization. That's a procedure called renormalization, and it's a complicated story of how you're supposed to do that. It's not at all some straightforward squiggly arrow like this. And instead, that complicated procedure of renormalization was really systematized by Ken Wilson in the 1970s into something called the renormalization group, which you should think of as a flow equation on an infinite dimensional parameter space. Morally, it's something like a gradient flow for a Morse function on that space. That's more or less completely true in 2 dimensions. It's morally true elsewhere, but that's kind of what you should have in your mind, some kind of Morse flow, Morse function gradient flow on some infinite dimensional space of parameters. That's Wilson's renormalization group. And according to Wilson, a continuum quantum field theory is an RG trajectory. Well, it's either an RG fixed point or an RG trajectory emanating from a RG fixed point, which in this case usually goes by the name of the ultraviolet fixed point. And the idea is that the short distance physics of that quantum field theory is governed by the physics of the fixed point theory. And this trajectory is induced either by turning on a relevant operator of scaling dimension delta less than d, or moving out onto some moduli space of vacua, or both. From a renormalization group fixed point, right? So the idea here is that in the language of Morse theory, the unstable manifold is finite dimensional. Okay? So even though we're flowing in this infinite dimensional parameter space, to tell you which trajectory I'm on takes only a finite amount of data. Okay? That's a continuum quantum field theory according to Wilson. Okay? the Zamolodchikov C function, it really is a Morse function for this theory, right? Yeah. Well, I mean, it does in the sense that there's an expression for it in terms of the stress tensor, and at every fixed point, it's equal to the central charge of the Virasoro algebra for that conformal field theory. Well, right. So I mean, the renormalization group is actually scheme dependent, okay, and so there are actually choices involved in that, right? That's right. That's right. So, in any case, the whole upshot of all of this is that the first baby step on understanding quantum field theory is to understand the fixed point theories, the renormalization group fixed point theories. Back when I was a lad, the ultraviolet fixed point was always the free theory. This is called asymptotic freedom, okay? And that was what quantum field theory was for us back in the day. We now know that that's an extremely non-generic story. The typical story is that the ultraviolet fixed point is some renormalization group fixed point, which, as far as we know, is not the endpoint of some RG flow from some asymptotically free theory. Okay? And that picture that we had back, as I said, it's still prominent in all of the textbooks, is hopefully hopelessly atypical. Okay? And we're really interested in trying to get to the more generic situation, which for which supersymmetry will be tremendously helpful. The more supersymmetry, the more constrained these RG flows are, the structure of the theory is much more rigid, and you might think that we should start with the maximal amount of supersymmetry in 4 dimensions, namely n equals 4. That will be the subject of many lectures next week. It is, in some sense, the simplest of all quantum field theories. It's been called the harmonic oscillator. Of the 21st century, because the harmonic oscillator is the simplest of all possible finite dimensional dynamical systems. This is the simplest of all possible field theories. But for our purposes, this will be too simple. We're going to study things with half as much supersymmetry, namely n equals 2. So we'll still have a lot of control, but the phenomenology will be much, much richer. One of the features that's true here, and it is possible to arrange over here, is that, as I said, our theories come in families. So there are a non-trivial conformal manifold, or in the language of Wilson, there are exactly marginal deformations. And the idea is that the gauge theory beta function is one loop exact and if you have an n equals to, I'm sorry, have I knocked it off? Enthusiastic. Now I can hear myself. So the beta function is one loop exact. So if I have an SCFT with global symmetry F, I can gauge a semi-simple subgroup and the contribution of the superconformal field theory to the beta function is entirely determined by the two-point function of the conserved currents associated to that global symmetry, which determines a number which in the appropriate units is actually an integer that I'll call k. And if it turns out that that integer is 4 times the dual Coxeter number, that means that the corresponding, that gauge coupling is actually a renormalization group invariant and is a marginal parameter for a family of theories. So we write out that parameter, tau, because we'll use it later. Tau is theta over pi plus 8 pi I over g squared. So g is the gauge coupling. Theta is the coefficient of f wedge f integrated of the second Chern class of the bundle. And tau is a marginal parameter. If we manage to satisfy this requirement on k. How about we call this H check? And small k is this two-point function is determined by the operator product of two currents. In the operator product, there's a coefficient of the identity operator. In some units, that coefficient is an integer, which I'm calling k. Okay? Right. It's the dual Coxeter number of whatever it is I'm gauging, or some simple factor in that group. So I need to do this for each simple factor that I gauge. Right? So that means that it's a tangent to some conformal manifold. Right? Right. So it's, rather than a fixed point, I have some fixed manifold. Well, it's not a manifold as we just discussed, but whatever. Right? Okay. Okay, so finally we get back to class S. Gayotto-Muranitsky and Davide Gayotto and then Gayotto-Muranitsky introduced a construction for producing a class of 4D n equals 2 superconformal field theories by compactifying a certain superconformal field theory in 6 dimensions on a Riemann surface with codimension 2 defect operators located at points on the Riemann surface. And so this description is just some codification of the data that went into their construction. And that's what we're going to discuss. And as we see from what's on the blackboard, we already have a conformal manifold, which I so cleverly erased, namely, in the untwisted case, just MGN. There's a whole nomenclature invented by Ken Wilson. Let's just use the word marginal, okay? There's marginally relevant, and there's all kinds of subtle, edge cases for which he has a terminology, but we're not going to bother with that, okay? So what I want to say is that for every Pants decomposition of our curve C, our punctured curve C, we'll get a presentation of this family of superconformal field theories as a gauge theory with 3g minus 3 plus n simple factors in the gauge group. different Pants decompositions give you different presentations of the same theory as a different gauge theory. So if you get bored or lost or whatever, you can entertain yourself by, so it gives a presentation of the gauge theory, and we'll call this an S-duality frame. And you can ask, how many S-duality frames are there? For the n-punctured sphere. Okay, so as I said, if you get bored, you can compute that. Okay? I'm about to say that. As I said, I'm supposed to, the marked points are included in the. I'm supposed to write it as a, those are one of the holes in the pair of pants, right? There's a Pants decomposition of unpunctured surfaces. There's also a Pants decomposition of punctured surfaces, right? Yes? Okay, so now what I want to say is sort of the structure of this theory near a component of the boundary of MGN, C degenerates. Let's say it's a separating pinch just for ease of exposition. So the curve separates into two pieces joined at the node where the original genus is G1 plus G2 and the original number of punctures is N1 plus N2 minus 2 because we've got these additional guys associated to the node where I glue things together. Generically, the nilpotent orbit at the node is the zero orbit, but not always. And I'll explain the not always in a second. But the idea is that when the curve does this, something similar happens to the conformal field theory. Namely, the superconformal field theory decomposes into a superconformal field theory associated to the guy on the left, a superconformal field theory associated to the guy on the right, and free vectors associated to the node. Turning back on the gauge coupling, moving away from the boundary, corresponds to now gauging some subgroup of the global symmetry of this guy and the global symmetry of that guy, such that the total K is 4 times the dual Coxeter number of that thing that we gauged. Clearly, if you go to a 3G minus 3 plus n-fold self-intersection of the boundary, you completely degenerate the surface into 3 punctured spheres, glued together by cylinders. And to classify such theories, what we need to do is understand what we should attach the superconformal field theory we should attach to the three-punctured sphere. And how they can be gauged. And then you can take these ingredients and put them together in an arbitrarily complicated way, reminiscent of the child's toy, which I hope is familiar to at least a couple of people in the audience. Tinkertoys was the other part of my title. It's a child's toy, which this story is very reminiscent of. So if you haven't seen them, you can at least find pictures on the internet of what they look like. Okay. Now, this story isn't quite right. Because there are some degenerations where you have a genus 0 guy on one side of the node, and it could be more than, so this is what the degeneration you get when two of the punctures collide. In general, you could have more than two, but it suffices to explain this case. Once you understand this case, the other ones are easy to understand. Where for particular choices of the pair of nilpotents which collide such that there's no SCFT corresponding to a three-punctured sphere with that pair of nilpotent plus any third nilpotent in your catalog of nilpotents that you're allowed to choose from. There's just no such theory. And we need to just have to, by hand, add some additional wooden spools to our Tinker toy. And we gave these the rather infelicitous name of irregular fixtures. And they play a small role in the whole story. So let me describe a little bit the generic situation, and then it will be clear what's interesting. So the usual story is that we get the 0 orbit at the node, and the gauge group is G, where G is the compact Lie group associated to script G. Right? So I described script G as the thing, that describes how what twist you have around some puncture, right? Well, okay, there's a puncture. It's in the 0 orbit of that Lie algebra, and the gauge group that gets turned on is the corresponding compact Lie group. Okay? So this is the generic situation. What happens there is that instead of, you might not get the 0 orbit, you might get some other orbit, O, and instead of G, you get some group H, where H is a subgroup of something I haven't defined because I'm really badly organized, the flavor symmetry group associated to that nilpotent, O, which is a subgroup of G. And I probably won't get to explain the recipe for what f of O is until next time, but it's some subgroup of G, and H in turn is a subgroup of that. Okay. Oh, well, actually, I did explain it here. The corresponding Lie algebra, f of O, is the centralizer. I see I was more organized than I thought, of the homomorphism from SL2 into G, which defines that nilpotent orbit, right? There's an equivalence between nilpotent orbits and homomorphisms from SL2 up to conjugacy. So the centralizer of that homomorphism is the thing I call little f, and capital F is the corresponding compact Lie group. Okay? So far, so good? So that's a lot of... I should explain that I'm laying out a lot of black box statements here. One second, let me just finish the sentence. Many of which I will explain next time. So please don't feel that everything I say is complete voodoo. Some of it is only partial voodoo. Yes, sir. Indeed. In that case, you always get the generic situation. That's yeah. So you'll always get the surface doesn't split into two, but you do get two extra. You lose one in the genus, and you do get two extra marked points. The marked points are always the zero orbit, and the gauge group on the associated to the node is always G. Okay. So that's the generic situation, and that will also play a role. But let me do the simplest possible case of this construction where we get a family, namely the four-punctured sphere. After all, if we can't understand that, we're not going to understand anything more complicated. So let's just study the four-punctured sphere for a second. And let's take the untwisted case, so this bundle P is trivial, okay, and just study that story. So, of course, we have the moduli space of four punctured spheres, which is CP1 minus the points 0, 1, and infinity. We can parameterize that by the cross ratio of the 4 points. And there are, in this case, 3 S-duality frames associated to the different Pants decompositions of the four-punctured sphere. So the one adapted to, I'm not sure which way to draw it. I'll draw it for variety as a long cylinder rather than as a pinch. So if I put Z1 and Z3 over here, and Z2 and Z4 over there, this is the S-duality frame adapted to X goes to 0. And if I call Q e to the I pi tau, this is the formula. So let me write f of tau as, this is definition, as minus a ratio of 4th powers of theta functions, I claim that's just the cross ratio x. Okay, so what I wanted to do here was relate the gauge theory description to the moduli space of punctured Riemann surfaces description. And here I've told you what the relationship is. It's, of course, as we'll discuss presently, many to one. But f of tau is a map from the fundamental domain of a certain congruent subgroup of PSL2Z to M04, parameterized by the cross ratio. And that tells you how the gauge coupling is to be read off. So in particular, F takes the fundamental domain for gamma of 2 and mapped it to M04, where gamma of 2 is generated by t squared, which takes tau to tau plus 2, and s, t squared s, which takes tau to tau over 1 minus 2 tau. The first thing is obvious. Theta is an angle, and so shifting theta by 2 pi does nothing to the theory. Let me just finish the sentence. But the second one should shock you to your core, okay? At least if you're a physicist. If you're a mathematician, it seems like nothing, okay? But what is some incredible non-perturbative statement about this gauge theory. Namely, if you replace, theta and g squared by this thing, the physics is absolutely isomorphic. Moreover, this is true not just for one particular gauge theory, which you might, by dint of many calculations, convince yourself is a reasonable thing to say, but it's true of every possible gauge theory that is realized in this way, as a 4-punctured sphere in class S. Okay? This is a shocking statement. I pause for 30 seconds to let the shock sink in. Okay? This is a really shocking statement, but it is, essentially a trivial consequence of saying that the physics is realized in this way. If it turns out that two of the punctures are the same nilpotent orbit, if two punctures are the same, say for instance the guys at Z1 and Z2, then the symmetry is larger. It's gamma 0 of 2, where the extra generator is S, which normally takes tau to minus 1 over tau, which acts on the x plane as x goes to 1 over x. And now theories which are related by S are isomorphic. And if 3 of the punctures are the same, then the full PSL2Z generates isomorphisms of the quantum field theory. Yes, sir. Two punctures decorated by the same nilpotent orbit, right? So I can't tell the difference when I swap them, right? So we're here. The theta 2 to the squared. No, it's fourth powers. I said fourth. My trouble is I can think the right thing, say the right thing, or write the right thing, but rarely all three at once. So you're lucky if you get 2 out of the 3. Okay. Thank you. This is also good. I know somebody's awake in the audience. Okay. Where were we? Yes. full SL2Z. So what I want to do now, in whatever time remains me, is do something which will be useful, hopefully, in Lottie's lecture to follow, which is study something about the moduli space of vacua of these theories, and a particular component of it called the Coulomb branch, whose geometry is determined by a certain complex integrable system, which in the case of these class S theories is a Hitchin system. Okay? And so we will have a brief foray back into Hitchin systems for what remains of this lecture. Okay. So, right, so the Coulomb branch, the ultra-long distance physics is just free U1 to the rank gauge theory. And if you go a little bit away from the ultra far infrared, you get, as I said, some physics that Seiberg and Witten told us was governed by some complex integral system, namely a Hitchin system. And in this case, it turns out it's a parabolic Hitchin system on the curve C. So what I'd like to do is explain exactly how that arises. So the Higgs field phi has poles at the punctures with nilpotent residues which are not what you'd think from having read over there. O is a nilpotent orbit in G. The nilpotent residue is given in terms of the Spaltenstein map D, which takes nilpotent residues in G to nilpotent orbits in G to nilpotent orbits in the Langland's dual of G, and it has the property that D cubed is D. Phi is the Higgs field, which was featured in countless lectures earlier this week, right? And so it's a endomorphism valued one form on C with poles with nilpotent residues that I'm about to describe at the punctures, right? And so in the untwisted case, so little gamma is the identity. Phi of Z is just n, where n is a nilpotent in D of O, n over Z plus regular. And in the twisted case, let me just talk about the Z2 twisted case, because otherwise things are really confusing. Phi of Z is n over Z plus m over the square root of Z plus regular, where n is in D of O, which is an element of the set of nilpotent orbits in the invariant subalgebra. And here, M lies in the anti-invariant guise. So the point is, phi is supposed to change sign as you go around, as you circle the puncture. And the first thing changes, excuse me, what was it? Yeah, that's right. Sorry, phi is supposed to be invariant. So N is invariant, so this is single valued. M changes sign as you go around the puncture, but so does the square root of z, so that's also single valued, so that's something you can also have. And then you have non-singular terms. So that's what phi looks like. And what I'd like to do in the time that remains us is actually work out concretely a particular example. I will do it for an minus 1, which is the only case that I'm going to attempt to do here. It's an order reversing map on the set of nilpotent orbits. Okay, so there's a partial ordering by orbit closure. This is an order reversing map, and it's cubes to itself. I can't. I told you I can only do small 10 Stein. There. J plus, the invariant subalgebra, right? Which is a subalgebra of J, right? Okay. Fortunately, Lottie will explain that. You knew this was going to happen, didn't you? You just didn't know when. I'm hoping she'll explain. What I hope to do is present an example, right, which she can then explain. Okay, so hopefully having a concrete example, there will be something, you know, to wrap your hands around. Okay, so that's going to be my excuse for the otherwise shoddy bit of pedagogy. Let's erase this here. Okay, so what I'm going to do is take the simplest possible case, namely J is a n minus 1, the 4-punctured sphere, and P is trivial, so no twists. And I'm going to put two copies of the subregular representation and two copies so the subregular orbit and two copies of the trivial orbit, the zero orbit. So I should say orbits in an minus 1 are partitions of n, and this mysterious map that I seem in real time to be unable to spell is simply the transpose partition, right? So you write the partition as a Young diagram and then you flip it on its side, okay? D just takes O to the transpose of O. So in particular, D of n minus 1, 1 is 2, comma 1 to the n minus 2, and D of 1 to the n is n, also known as the regular nilpotent. So far, so good? Okay. Now let me give the locations of these guys. I'll call this Z1, this is Z2, this is Z3, this is Z4. And I'm going to be interested in the spectral curve, which is given by setting the determinant of lambda times the identity minus phi equal to 0. I can write this as lambda to the n minus a sum of lambda to lower powers times symmetric polynomials. And the phi k's, if you work it out, are just uk, some parameter, z13, z24, z34 to the k minus 2, dz to the k, over z minus z1, z minus z2, z minus z3 to the k minus 1, z minus z4 to the k minus 1. And if we use, so the expression I wrote down is complicated looking, but has the advantage of being explicitly Mobius invariant. So we can use Mobius symmetry to set Z1, Z2, Z3, and Z4 to 1, f of tau, 0, and infinity. And then this expression over here just becomes uk dz to the k, z to the k minus 1, z minus 1, z minus f of tau. And so the spectral curve is given by this equation with these expressions for the z sub k's. There are n minus 1 parameters, which is the dimension of the Hitchin base in this case. Right? The n minus 1 parameters are the u sub k's. What I want to do now is examine what the physics of this theory looks like near the various degenerations of the curve C. When f of tau goes to 0 and infinity, then what happens to the curve is that we have an n minus 1, the subregular nilpotent and the 0 orbit on one side, and another copy of the subregular nilpotent and the 0 orbit on the other side. The thing that connects them is the 0 orbit, and this, I claim, is a famous conformally invariant n equals 2 Lagrangian field theory, much studied in the late 1990s. Well, theories of this sort were studied in the late 1990s, and in particular, the Seiberg-Witten solution for this thing is well known, and this is a succinct, in fact, a much easier way to derive it than was originally done. But now, and we can do something interesting, which nobody had the guts to try to do. F of tau is the cross ratio, which as in this language is just Z2. I'm not sure I copied this. Did I write this right? Let me see, make sure I wrote this right. Yeah, no, I think I wrote this right. Yeah, I think it's Z. I'm pretty sure it's Z2. So Z2 approaching either 0 or infinity means one of the subregular guys approaching one of these full guys, right? There are two different ways to do that. Those are f of tau goes to 0 and f of tau goes to infinity. Sorry? And it looks like that when we do things. The other limit is f of tau goes to 1, where Z2 approaches Z1, which looks different, right? That's where the two subregular guys end up on one side of the pinch, and the two 0 and the two 1 to the ends end up on the other side of the pinch. Okay? There are different SUNs, that's right. Absolutely. They're highly non-trivially related to each other. But the physics is isomorphic, right? It's that extra, it's erased now, but that extra S transformation that I said appeared when two of the punctures were the same. That's tau goes to minus 1 over tau, which is exactly what x goes to 1 over x does. Okay? When f of tau goes to 1, what we have on this side of the pinch are the two subregular guys. And on this side of the pinch, we have the two 0 orbits. And what connects them is this irregular situation that I discussed before, namely, we get an SU2 gauge theory, and the orbit is not the 0 orbit, but rather is that orbit n minus 2, 1 squared. Yes? Great question. I will try to explain as much of this as possible in my next lecture tomorrow morning. I just wanted to present the answer this time so that Lottie, if she chose to, might make use of it. But I will try to explain the technology. So right now, this is all black box voodoo, okay? Hopefully, it will be slightly less black. It will still be voodoo, but slightly less black box at the end of my second lecture. Okay? But you'll just have to trust me that I did this much right. But let me tell you what we get over here. This is an SU2 gauge theory, and there's a hypermultiplet in the fundamental representation of SU2 on this side, and what appears over here is a certain isolated interacting SCFT of rank n minus 2, and it has a global symmetry F, which is SU2n at level k equals 2n cross SU2 at level k equals 6, which is enhanced to E6 at level 6 for n equals 3. Sorry? That's not visible, so let me write it someplace else. I probably shouldn't be writing there anyways. Should be some rule against that. Enhanced. So F is enhanced to E6 at level 6 for n equals 3. Okay? So this is, and I should have said, lambda is the Seiberg-Witten differential. We've written down the spectral curve, often called the Seiberg-Witten curve, and the geometry of the Coulomb branch is determined from that data in a way that Lottie will, of course, describe in eloquent detail during her lectures. And that, I think, is a good place to end today. I managed to get through much faster than I thought. That's really good. Okay. Thank you.
Questions?
I just notation. When you write n minus this partition, you're just giving the Jordan blocks, right?
That's right. So indeed. So we're talking about a nilpotent orbit. So in particular, I can think of it as a representative is guys which are ones just above the diagonal. And the Jordan blocks, the sizes of the Jordan blocks are these numbers. Another way to say it, if you want to think about it in terms of embeddings of let's do SU2 into the compact group since we're friends. What I'm interested in is the decomposition of the fundamental representation under this embedding of SU2. So I have to give you a set, each irreducible SU2 representation is specified by uniquely by its dimension. So I just have to tell you how n decomposes into a sum of SU2 representations, right? And so that more or less works for all of the classical Lie algebras. I say more or less because for D2n, right, SO4n, okay, there are actually two nilpotent orbits corresponding to what are called very even partitions, ones where all of the entries are even numbers, okay? And what I mentioned earlier, but it went by so fast you've long since forgotten, is that under the outer automorphism of D2n, those very even guys get swapped. Okay. What this has to do with is the fact that the spinor representations are pseudo-real, and they get exchanged under parity. Okay, and so it's not enough to tell you how the vector representation decomposes. You need to know how the spinor representations decompose, and there are two choices in the case of a very even nilpotent. Right.
More questions? So I had a question. You mentioned that there's a general picture where the Hitchin system emerges in the special case, but in general, when you move away from the ultraviolet fixed point, there's a general picture involving a description in terms of complex integrable systems.
Right, so, indeed. So let's talk about the deformations of these theories for a little bit. So I said I was just going to concentrate on the renormalization group fixed point theory, the superconformal theory, right? So what can you do to deform that? There are two things you can do. One of them is move out onto one of these components of the moduli space of vacua. So Lottie is very quickly going to move out onto the Coulomb branch, and it probably never return. But there are other branches. There's something called the Higgs branch, which is a very interesting hyperkähler space. And there are various mixed branches and so on. If you move out onto that, you get an RG flow, so that the UV theory is the original superconformal theory. In the far infrared, you get something whose physics is governed by this integrable system. The other kind of deformation you can do is turning on relevant operators in the theory, so to speak, adding them to the action, even when I don't have an action. Okay? And what that does is it changes, it lifts some of the flat directions in the moduli space of vacua, and changes the geometry of the ones that remain. So in particular, you can study the Seiberg-Witten geometry not just for things analogous to the example that I did, but to the mass-deformed case where you add masses for the fundamental hypermultiplets. And in fact, that was the way people usually did things in the late 90s when this was a whole cottage industry. They studied these solutions as a function of the hypermultiplet masses and checked that, when you sent some mass to infinity, you got the same, the expected result with fewer hypermultiplets. And when you sent it to zero, there are various sorts of limits you could check, which here, because I can more or less write down the Seiberg-Witten curve by inspection, I don't care so much about doing elaborate checks on my computation because the computation was trivial.
In the twisted case, the description of the Coulomb branch, does it involve the G Hitchin system globally?
No, it's always the J Hitchin system, but it's a kind of twisted J Hitchin system where I erased the formula. The Higgs field has that peculiar behavior at the locations of the punctures where the nilpotent sits, the residue simple hole sits in in the invariant, and it's a nilpotent in the invariant part of J, right? But then you can also have this square root coefficient of 1 over square root of Z in the anti-invariant part. And that's sort of some arbitrary point in the invariant.
Do you think there could be an equivalent description in terms of the G Hitchin system?
No. You really saw, this is really a J-valued a Higgs field, J-valued Higgs field. J-valued. I had it right the first time. J-valued Higgs field. It's just that its behavior at the punct. More generally, it has to transform correctly when I go around any cycle on the Riemann surface. So I'm doing genus 0. Once I've told you how it behaves when going around the punctures, I'm done. On higher genus, then there's a little bit more data because it needs to transform correctly when you go around some handle. Okay, but it's always a J Hitchin system, not G. Uh-huh. Correct. You get G on a half space, right? Right. So I don't know whether you want to be working on a half space or not. You can. I spend some of my time working on a half space, but you get G SUN Yang mills on a half space, right?
From there, if you try to go to 3D by compactifying on C,
right.
It doesn't seem unreasonable to expect there would be a description in terms of G.
Well, as I said, as far as I understand, it's the J Hitchin system, but perhaps with peculiar, monodromy conditions when you go around cycles on the surface.
Could it be that you're saying that there's a double cover, either of the basic curve or of its special cover, and you're having a G Higgs bundle on the double cover that needs to transform?
Well, it's, as I said, I think it's a J Higgs bundle, but with certain transformation properties under the deck transformations.
If we just look at 3 punctured spheres,
yes,
if you're given 3 distinct orbits,
right?
Is it known what the physical description of each of those 3 punctured spheres would?
I write very long papers tabulating the answer to that question. In fact, sometimes the answers are so long that I can't tabulate them in a paper. Instead, I write a web application where you can, find out the answer. So, in fact, since I have the time, let me make a plug for the E7 and E8 versions of this story. You can go to the following URLs. Same URL, just the last thing has changed. And while away the hours, exploring all of the 3 punctured spheres in E7, this E7 and E8 theory. If we both tell you what all of the 3 punctured spheres are and all of the 4 punctured spheres and their S-duality frames, let me warn you that if you thought YouTube was a time killer, in the E8 theory, there are 250,000 4-punctured spheres. So, you know, cat videos really were nothing compared to the time you could waste on this website. Okay.
So I wanted to ask you sort of another a broad philosophical question. So at the beginning you had this motivation, if I understood correctly, the motivation is to understand some moduli space of quantum field theories of a certain type.
Right.
So for the mathematicians here, could you sort of say what would be a dream statement or picture that one would like to have, say, for these theories of class S?
Well, so one of the things which we learned about here, I even paused for 30 seconds to hopefully help you appreciate how miraculous it was, is the appearance of these S-dualities. So different numbers, so different Pence decompositions of the surface gave you different presentations of the same family of theories as gauge theories, right? So did anybody get bored and work out how many S-duality frames there are for the n-punctured sphere? Sorry? Well, it's 2n minus 5 double factorial. Okay. Anyway, so that tells you there are a huge number of different ways of describing the same physical theory as a gauge theory. Okay, and that, among many other things, I think is an interesting lesson. Okay, and part of what I want to do, sort of as a kind of big picture thing, is stare at this large class of theories that we've constructed and try to learn some lessons. Okay, you know, you're exploring some new territory, and you know, maybe you'll find something new and surprising that you didn't expect, and hopefully thereby, you know, get some better handle, you know, to get some more intuition for quantum field theory generally. I don't really care that much about n equals 2 supersymmetric field theories per se. That's not the world we live in, but it's a place where I can learn things, some of which may hopefully carry over to the world that we live in. For the 4-punctured sphere, there are 3 descriptions. Double factorial. Double factorial, right? So, yeah, they are odd, as you can, 2n minus 5 double factorial, right? Means you skip every other number, right? So it's n double factorial is n times n minus 2 times n minus 3 times blah, blah, blah. No, no.
Any other questions? If not, let's thank Jacques again.
Okay.